Look up at the night sky, and you're seeing more than just stars. You're witnessing the invisible hand of magnetic fields shaping the cosmos. Picture this: a neutron star, spinning faster than a kitchen blender, shooting out beams of radiation so precise they flash like a cosmic lighthouse. Or imagine Earth's magnetic shield bending the fury of the solar wind into shimmering auroras that dance above the poles. These aren't just pretty sights, they're proof that magnetic fields are the universe's silent architects, weaving order into chaos across billions of light years. From the birth of stars in swirling gas clouds to the explosive deaths of black holes, magnetic forces are everywhere, pulling strings behind the scenes. They guide cosmic rays like interstellar highways, twist galaxies into spirals, and even protect planets from deadly radiation. Over the next few minutes, we'll unravel 30 mind-bending ways these invisible fields sculpt the universe, some so powerful they can rip atoms apart, others so subtle they've hidden in plain sight for centuries. Stick around, because by the end of this journey, you'll never look at the night sky the same way again, ready to uncover the secrets written in magnetic ink across the cosmos. Let's dive in. Now let's zoom in on the very beginning of a star's life, where magnetic fields play the role of a cosmic sculptor. Deep within vast clouds of gas and dust, gravity tries to pull everything inward, but without magnetic fields, this process would be chaotic. Imagine a collapsing gas cloud as a swirling, turbulent mess. Gravity wants to crush it into a star, but left unchecked, the cloud would fragment into countless tiny clumps instead of forming a single, stable star. This is where magnetic fields step in. They act like invisible threads woven through the gas, channeling the chaos into order. As the cloud collapses, these fields slow down the spinning material, preventing it from flying apart. They also guide the gas into a flattened disk around the newborn protostar. Think of it like a cosmic potter's wheel, shaping the raw material into a precise form. Without this magnetic guidance, star formation would be far less efficient, and many stars might never ignite at all. Thanks to advanced telescopes like ALMA, we can actually see these magnetic fingerprints in action. ALMA observations reveal how dust grains align with magnetic fields, glowing in polarized light like tiny compass needles pointing the way. These snapshots show us the hidden architecture of star birth, proving that magnetic forces are the silent choreographers behind one of the universe's most spectacular dances. So the next time you gaze at a star, remember its very existence was shaped by the delicate balance of gravity and magnetism, a partnership written into the fabric of space itself. Now let's turn our attention to the Sun, where magnetic fields unleash some of the most violent explosions in our solar system. Picture the Sun's surface as a seething ocean of plasma, crisscrossed with invisible magnetic field lines. These lines twist and tangle like rubber bands stretched to their limit, storing unimaginable amounts of energy. When the tension becomes too much, they snap, releasing a solar flare with the power of millions of hydrogen bombs in just a matter of minutes. These eruptions aren't just spectacular light shows. They send shockwaves through space, hurling charged particles at nearly the speed of light. When directed at Earth, these particles collide with our planet's magnetic shield, creating dazzling auroras, but also posing serious risks. A powerful flare can disrupt satellites, knock out power grids, and even interfere with GPS signals, throwing off navigation systems worldwide. The infamous Carrington event of 1859, for example, sparked fires in telegraph stations and lit up skies as far south as the Caribbean. Modern technology makes us even more vulnerable. A flare like that today could black out entire continents for weeks. That's why scientists closely monitor the Sun's magnetic activity, using spacecraft like the Solar Dynamics Observatory to capture stunning high-resolution images of these explosive events. By studying how magnetic fields twist and reconnect, we're learning to predict space weather, giving us a fighting chance to shield our technology from the Sun's fiery temper. So while solar flares remind us of the sun's raw power, they also highlight the delicate interplay between cosmic magnetism and life on Earth. Next time you check your phone or admire the northern lights, remember both are shaped by the same invisible forces. Now let's zoom out from our solar system and take a galactic perspective. Magnetic fields don't just shape stars and planets, they weave through the vast spiral arms of galaxies like invisible threads, guiding the dance of cosmic gas and dust. Picture the Milky Way, our home galaxy, with its elegant spiral arms stretching across the night sky. Those swirling lanes aren't just pretty patterns. They're cosmic highways where magnetic fields align with the spiral structure, channeling gas and dust into dense clouds that eventually collapse into new stars. Scientists have mapped these galactic magnetic fields by studying polarized radio waves emitted by electrons spiraling along the field lines. The result: a stunning magnetic fingerprint that traces the Milky Way spiral arms. These fields act like cosmic traffic controllers, preventing gas from drifting aimlessly and instead funneling it into star-forming regions. Without them, galaxies might lack the organized structure we see today, and star formation could be far more chaotic, but the influence doesn't stop there. Magnetic fields also help stabilize spiral arms against the gravitational pull of the galaxy's rotation, keeping those iconic shapes intact over billions of years. In galaxies like Messier 51, the Whirlpool Galaxy, astronomers have observed magnetic fields tightly wound along the spiral arms, reinforcing their structure. It's a subtle force, but across cosmic time, magnetism helps sculpt the grand designs we admire through telescopes. So next time you gaze at a spiral galaxy, remember, those sweeping arms aren't just shaped by gravity. Invisible magnetic fields are quietly at work, orchestrating the flow of matter and the birth of stars on a scale almost too vast to comprehend. Now let's turn our attention to one of the most extreme environments in the universe: neutron stars. These incredibly dense remnants of supernova explosions pack the mass of our sun into a sphere no bigger than a city. But what makes them truly spectacular is their mind-bending magnetic fields, trillions of times stronger than Earth. These ultra-strong fields don't just sit there, they act like cosmic particle accelerators, channeling charged matter into narrow jets that blast outward at nearly the speed of light. Imagine a fire hose of energy so intense it can carve through space itself. These jets are what give us pulsars, neutron stars that beam radiation like interstellar lighthouses as they spin. A perfect example is the Crab Nebula's pulsar, the spinning heart of a star that exploded nearly 1,000 years ago. Its magnetic field whips particles into such frenzy that they emit beams of light, radio waves, and even gamma rays, the most energetic form of light in the universe. When these beams sweep past Earth, we detect them as rapid pulses, hence the name pulsar. But sometimes neutron stars take it even further. When their magnetic fields become too twisted, they can trigger colossal gamma ray bursts, some of the most powerful explosions since the Big Bang. These bursts release more energy in seconds than our sun will in its entire lifetime. So while neutron stars may be small, their magnetic fields are anything but. They shape the very fabric of space around them, proving that even in the cosmos, the smallest things can have the biggest impact. Now let's zoom in from the cosmic extremes of neutron stars to something much closer to home, Earth's own magnetic shield. While our planet's magnetic field might seem tame compared to the trillion-Gauss monsters of neutron stars, it plays a life-saving role every single day. Picture Earth's magnetosphere as an invisible force field, stretching tens of thousands of kilometers into space. This dynamic bubble is created by the churning of molten iron in our planet's core, a process known as the geodynamo. But it's not just a static shield, it's constantly battling the solar wind, a relentless stream of charged particles hurled our way by the sun. Without this magnetic defense, that solar wind would strip away our atmosphere over time, leaving Earth as barren as Mars. Instead, the field deflects most of these particles, funneling them around the planet like water flowing around a rock in a river. Some get trapped in the Van Allen belts, two donut-shaped zones of radiation that wrap around Earth. These belts act like cosmic storage units, holding the particles at bay and preventing them from reaching the surface. But sometimes the sun fights back harder. During intense solar storms, the magnetosphere can get overwhelmed, leading to geomagnetic storms. These disturbances can disrupt satellites, knock out power grids, and even create stunning auroras near the poles as the solar wind slips through the cracks. The most famous example, the Carrington event of 1859, when a solar superstorm sparked auroras as far south as the Caribbean and fried telegraph systems worldwide. So while Earth's magnetic field might not be the strongest in the universe, it's perfectly tuned to protect life as we know it, a silent guardian against the chaos of space. Now let's venture beyond Earth's protective bubble and into the vast expanse of our galaxy, where magnetic fields take on an entirely different role, shaping the paths of cosmic rays. These aren't your everyday rays of light. Cosmic rays are high-energy particles, mostly protons and atomic nuclei, racing through space at nearly the speed of light. But here's the twist: by the time they reach us, their original paths are completely scrambled. That's because galactic magnetic fields act like cosmic pinball machines, bending and twisting these particles as they travel. Imagine throwing a straight punch in a room full of magnets. Your fist would get yanked in all directions. That's exactly what happens to cosmic rays over millions of light years. This deflection makes it incredibly hard to trace them back to their sources, turning their origins into one of astronomy's biggest puzzles. Are they flung out by supernova explosions, ejected from the violent cores of active galaxies, or perhaps accelerated by something even more exotic? To crack this mystery, scientists rely on massive detectors like the Pierre Auger Observatory in Argentina. This facility spans an area the size of Rhode Island, with over 1,600 water tanks designed to catch the faint showers of particles created when cosmic rays slam into Earth's atmosphere. By studying these showers, researchers can estimate the rays' energy and direction, but even then, the galactic magnetic fields leave their fingerprints, muddying the trail. So while these fields might not be as visible as auroras or as intense as a magnetar's grip, their subtle influence shapes our understanding of the universe's most energetic particles. And as detectors grow more sensitive, we're inching closer to unmasking the cosmic accelerators hidden in the magnetic maze of our galaxy. Now, let's zoom in on one of the most extreme environments in the universe, the swirling chaos around a black hole. Here, magnetic fields don't just influence matter, they dominate it. Picture a vast, glowing disk of superheated gas spiraling toward the black hole's event horizon, like water circling a drain. But this isn't just any disk, it's an accretion disk where magnetic fields twist and tangle, creating turbulence so intense it heats the plasma to millions of degrees. This magnetic chaos doesn't just cook the gas, it also launches some of it away at nearly light speed in the form of dazzling jets. These jets, stretching thousands of light years into space, are cosmic power lines, channeling energy from the black hole's grip into the wider universe. The best example, the supermassive black hole at the heart of Galaxy M87, famously photographed by the Event Horizon Telescope. Simulations of this monster reveal how its magnetic fields act like a cosmic slingshot, flinging particles outward in narrow, focused beams. Without these magnetic forces, accretion disks would be far quieter, and the universe far less dramatic. So next time you see an image of those brilliant jets piercing the darkness, remember, it's the invisible hand of magnetism turning chaos into cosmic fireworks. Now let's turn our attention to one of the most bizarre and powerful objects in the cosmos, magnetars. These aren't your average neutron stars. Imagine a stellar remnant so dense that a teaspoon of its material would weigh 1 billion tons, then crank its magnetic field up to 1 trillion times stronger than Earth. That's a magnetar, a cosmic powerhouse where magnetism reaches almost unimaginable extremes. These ultramagnetic stars don't just sit quietly. They unleash violent starquakes where their crusts crack under intense magnetic stress, releasing energy equivalent to millions of nuclear bombs in mere milliseconds. But the real showstoppers are their soft gamma ray repeats sudden, unpredictable bursts of high-energy radiation that flicker like cosmic strobe lights. One of the most dramatic moments came in 2004, when a magnetar 50,000 light-years away let out a scream so powerful it briefly ionized Earth's upper atmosphere, even though the star was halfway across the galaxy. Satellites detected the pulse, and for a split second, our planet's outer layers trembled in response. Magnetars remind us that the universe is far from static. It's a place where invisible forces can reach across unimaginable distances, shaking the very fabric of space itself. And if that doesn't make you pause, just wait, because magnetism has even more surprises in store. Now let's zoom out from these extreme cosmic powerhouses and take a closer look at the quieter, yet equally fascinating spaces between the stars. The interstellar medium, that vast, diffuse ocean of gas and dust, might seem empty at first glance, but it's anything but. Here, magnetic fields play a subtle yet crucial role, shaping the very fabric of this cosmic environment. These invisible forces weave through the thin gas, guiding the movement of particles and even influencing how dust grains align. Picture countless tiny compass needles all pointing in the same direction, thanks to the gentle tug of magnetism. This alignment isn't just for show, it polarizes starlight, leaving a telltale signature that astronomers can detect. The Planck telescope, with its keen eye for detail, has mapped this polarized light across the Milky Way, revealing intricate patterns that trace the hidden magnetic fields threading through our galaxy. But magnetism's influence goes deeper. It helps structure the interstellar medium, preventing chaotic turbulence from scattering gas too wildly. This orderliness is key to chemistry in space, as molecules form more easily in these magnetically shaped regions. Without these fields, the delicate dance of atoms and dust that eventually leads to star formation might never happen. So while magnetars show us the explosive side of cosmic magnetism, the interstellar medium reminds us that even in the quietest corners of space, magnetic fields are hard at work, shaping, guiding, and setting the stage for the next generation of stars. And as we'll soon see, their influence stretches even further. Now, let's bring the cosmic dance of magnetic fields a little closer to home, right above our heads, in fact. Few sights in nature are as mesmerizing as the auroras, those shimmering curtains of light that paint the polar skies. But what's really behind this dazzling display? It all comes down to Earth's magnetic field acting like a cosmic funnel. When the sun sends a gust of charged particles our way, Earth's magnetic field deflects most of them. But near the poles, where the field lines curve downward, these particles get channeled into the upper atmosphere. There, they collide with oxygen and nitrogen molecules, transferring energy and setting the sky aglow with vibrant hues: green, red, and even purple. It's a delicate balance of physics and beauty, a direct conversation between our planet and the sun. But Earth isn't the only show in the solar system. Jupiter, with its monstrous magnetic field 20,000 times stronger than ours, takes auroras to another level. The gas giant's polar lights aren't just driven by solar wind, they're supercharged by particles ripped from its volcanic moon, Io. These auroras aren't fleeting, they're permanent, radiant, and so powerful they'd outshine our own by orders of magnitude. Hubble's ultraviolet eyes have captured these colossal light shows, revealing just how intense magnetism can shape a planet's sky. So whether it's the serene glow over an Arctic horizon or Jupiter's relentless celestial fireworks, auroras remind us that magnetic fields don't just sculpt the cosmos, they light it up. And as we'll see next, their influence reaches even into the coldest, darkest corners of space. Now, let's shift our gaze to the cosmic cradles where stars are born, molecular clouds. These vast, dense regions of gas and dust are the nurseries of the universe, but without magnetic fields, they'd collapse under their own gravity long before stars could form. Here's how it works. Gravity constantly tries to pull these clouds inward, but magnetic fields push back, creating a delicate tug of war. The fields thread through the gas like invisible scaffolding, slowing down the collapse and giving stars time to take shape. Observations from the Herschel Space Telescope reveal something even more fascinating. These clouds aren't just chaotic blobs. They're structured into intricate filaments with magnetic fields running along their lengths like cosmic spines. Herschel's infrared vision showed us that stars often form at the intersections of these filaments, where gravity finally wins out. Without magnetic fields, these clouds would fragment too quickly, scattering their material before stars could ignite. Instead, the fields act as cosmic architects, guiding the gas into the right conditions for stellar birth. So the next time you look up at the night sky, remember, those twinkling stars owe their existence not just to gravity, but to the silent, invisible force of magnetism holding their nurseries together. And as we'll see, this magnetic influence doesn't stop at star formation. It shapes entire galaxies. Now, let's turn our attention to the Sun's invisible hand shaping the space around it, solar wind acceleration. The Sun doesn't just shine light into the solar system, it also blasts out a relentless stream of charged particles, and magnetic fields are the engine behind this cosmic wind. Here's what's happening. The Sun's magnetic field doesn't stay neatly organized. It twists, tangles, and sometimes snaps, flinging charged particles away at incredible speeds. These particles race outward, forming the solar wind, which carries the Sun's influence far beyond the planets. But without magnetic fields, this wind wouldn't have the punch it does. They act like cosmic slingshots, accelerating particles to over 1 million miles per hour. Recent discoveries from the Parker Solar Probe have given us a front-row seat to this process. Flying closer to the Sun than any spacecraft before, it's revealed how magnetic waves, ripples in the Sun's field, give the solar wind an extra push. Think of it like ocean waves propelling a surfboard, but on a solar scale. These findings help explain why the solar wind speeds up as it moves away from the Sun, something that puzzled scientists for decades. This magnetic-driven wind doesn't just flow aimlessly, it shapes the entire heliosphere, a giant bubble around our solar system that shields us from interstellar radiation. Without it, harmful cosmic rays would bombard the planets, making life as we know it far more challenging. So the next time you feel a breeze, remember, there's a far more powerful wind sculpted by magnetism rushing through the solar system. And as we'll see, this magnetic influence stretches even further into the heart of galaxies. Now, let's zoom out from our solar system and into the vast expanses between galaxies, where magnetic fields take on an even grander scale. Galaxy clusters, the largest structures in the universe held together by gravity, are also threaded with immense, invisible magnetic fields. These fields might be faint, but they stretch across millions of light years, weaving through the hot gas that fills these cosmic metropolises. So how do we detect something so subtle yet so enormous? The answer lies in synchrotron radiation, a type of light emitted when high-speed electrons spiral around magnetic field lines. This faint glow, often picked up by radio telescopes, acts like a cosmic fingerprint, revealing the presence of these hidden fields. Without them, the superheated gas in clusters reaching temperatures of tens of millions of degrees would simply dissipate into the void. But these magnetic fields do more than just leave traces of light. They play a crucial role in confining and shaping the cluster's gas, like an invisible scaffold holding everything together. Without this magnetic scaffolding, the turbulent motions within the gas would tear it apart, disrupting the delicate balance that keeps these clusters stable. What's even more fascinating is that these fields might be ancient relics stretching back to the early universe. Some theories suggest they were amplified over billions of years by the motion of gas and galaxies, while others propose they were seeded by powerful jets from supermassive black holes. Either way, they're a reminder that magnetism isn't just a local phenomenon. It's a force that shapes the universe on the largest scales imaginable. And as we'll see next, these magnetic fields don't just sit quietly. They can unleash incredible energy when they snap and reconnect, powering some of the most violent events in the cosmos. Now, let's dive into one of the most dramatic displays of magnetic power, magnetic reconnection. Picture this: invisible lines of magnetic force, twisted and stretched to their limits, suddenly snapping like overstretched rubber bands. When they break, they release an astonishing burst of energy, heating plasma to millions of degrees and flinging charged particles across space at incredible speeds. This explosive process isn't just a cosmic spectacle, it's the engine behind some of the most energetic events in the universe. On the Sun, magnetic reconnection triggers solar flares, eruptions so powerful they can outshine entire stars for brief moments. Closer to home, it's the same mechanism that lights up our polar skies, funneling solar particles into Earth's atmosphere to create the shimmering auroras we know as the northern and southern lights. But how does it work? Imagine two magnetic field lines running side by side but pointing in opposite directions. As they're pushed together, they suddenly break and reconnect in a new configuration, releasing pent-up energy in the process. It's like cutting a tensed rubber band. The snap sends energy flying in all directions. In space, this energy accelerates particles to near light speeds, creating bursts of radiation and violent plasma jets. What makes magnetic reconnection so fascinating is its dual nature, both destructive and creative. While it tears apart old magnetic structures, it also builds new ones, shaping the dynamic environments of stars, planets, and even galaxy clusters. Scientists are still unraveling its secrets, using satellites and supercomputer simulations to study how this process drives space weather and influences cosmic evolution. And as we'll see next, these magnetic fireworks aren't limited to our solar system. They play a role in some of the most extreme environments in the universe, from the jets of black holes to the hearts of distant galaxies. Now, let's turn our attention to a cosmic question that could hold the key to finding life beyond Earth: how magnetic fields might protect distant worlds. Imagine an exoplanet orbiting a fiery star, bathed in intense radiation. Without a magnetic shield, that world's atmosphere could be stripped away over time, leaving it barren and lifeless. But if it has a strong magnetic field like Earth's, it could deflect those deadly stellar winds, preserving its air and water, and maybe even fostering life. Scientists are especially intrigued by systems like TRAPPIST-1, where 7 Earth-sized planets orbit a small, cool star. Some of these worlds sit in the habitable zone, where temperatures might allow liquid water. But habitability isn't just about distance from a star, it's also about protection. If these planets lack magnetic fields, their atmospheres could be slowly eroded by the star's constant flares, even if they're in the right spot for life. Here's where things get fascinating. While we can't yet directly measure exoplanet magnetic fields, researchers use clues like atmospheric composition and stellar activity to guess their strength. For instance, if a planet shows signs of holding onto its atmosphere despite a violent host star, that could hint at a robust magnetic shield at work. The implications are huge. A magnetic field might be the invisible guardian that makes the difference between a desolate rock and a thriving alien world. And as we discover more exoplanets, understanding their magnetic defenses could help us pinpoint where life might actually have a chance. Up next, we'll explore how magnetic fields weave through the largest structures in the universe, cosmic filaments shaping the very fabric of space itself. Now, let's zoom out to the grandest scales of the universe, where magnetic fields weave through the cosmic web itself. Picture the universe as an enormous spider's silk, stretching billions of light years, with galaxies strung along vast threads of gas. These are cosmic filaments, the scaffolding of the cosmos, and magnetic fields play a hidden but crucial role in shaping them. Here's how it works. These filaments aren't just empty space. They're filled with ionized gas, and where there's moving charged particles, magnetic fields follow. Simulations like those from the Illustris project reveal how these fields help channel and stabilize the gas, guiding it into the dense nodes where galaxies form. Without magnetic fields, this cosmic web might look very different, with gas collapsing chaotically or dispersing entirely. What's even more fascinating is how these fields might influence the spin of galaxies. Some research suggests that the alignment of magnetic fields along filaments could nudge newborn galaxies into rotating in sync with the cosmic web itself. It's like an invisible hand gently shaping the universe's structure over billions of years. And while these fields are incredibly faint, far weaker than Earth's, their sheer scale makes them powerful players in the story of how the universe organizes itself. From the tiniest star forming clouds to these galaxy-spanning rivers of gas, magnetic fields are the silent architects of the cosmos. Coming up next, we'll see how astronomers use polarized light from quasars as cosmic compasses, tracing magnetic fields across the void between galaxies. Now, let's turn our attention to one of the universe's most brilliant beacons, quasars, and how their light helps us map the invisible magnetic fields stretching between galaxies. These distant powerhouses, fueled by supermassive black holes, send out intense beams of light that travel billions of light years to reach us. But it's not just their brightness that makes them special, it's the subtle twist in their light that holds the key. As this light journeys through space, it passes through vast clouds of ionized gas threaded with magnetic fields. These fields gently align the light's electric field in a specific direction, a phenomenon called polarization. By studying this polarized light, astronomers can trace the otherwise invisible magnetic fields that permeate the space between galaxies. Think of quasars as cosmic lighthouses, their beams flickering through a fog of magnetism, leaving behind clues about the structure of the universe itself. What's truly remarkable is how these measurements act like a compass for the cosmos. Just as a compass needle points north, the polarization of quasar light reveals the orientation of magnetic fields across unimaginable distances. This technique has uncovered fields in regions once thought to be empty, stretching across galaxy clusters and even the voids between them. Some of these fields might be relics from the early universe, fossilized remnants of turbulence from the birth of galaxies. And here's the kicker: these intergalactic fields, though incredibly weak, could influence how galaxies form and evolve over time. By bending the path of charged particles, they might steer gas into the right places for stars to ignite. So next time you hear about a quasar, remember, it's not just a distant light show. It's a messenger carrying secrets about the magnetic tapestry woven through the cosmos. Up next, we'll dive into the dynamo effect, the cosmic engine that generates magnetic fields in planets, stars, and even galaxies. Now, let's pull back the curtain on one of the universe's greatest hidden engines, the dynamo effect. This is the cosmic mechanism that breathes life into magnetic fields, from the molten heart of our own planet to the churning depths of distant stars. Picture a spinning, swirling fluid like molten iron in Earth's core or superheated plasma in the Sun, and imagine it as a colossal generator. As these conductive fluids move, they twist and stretch magnetic field lines, amplifying them like a self-sustaining power plant. Earth's geodynamo is a perfect example. Deep beneath our feet, the planet's liquid outer core churns as heat rises from the solid inner core, and Earth's rotation whips it into a frenzy. This motion converts kinetic energy into magnetic energy, creating the protective shield we call the magnetosphere. Without this invisible force field, solar winds would strip away our atmosphere, leaving Earth as barren as Mars. But the Sun takes this process to another level. Unlike Earth's relatively steady field, the Sun's magnetic activity follows an 11-year cycle, though it takes 22 years for its polarity to fully flip. During this dance, sunspots erupt, solar flares explode, and the entire heliosphere trembles with magnetic energy. The key difference: the sun's dynamo operates in its convection zone, where rising and falling plasma creates a turbulent, ever-changing magnetic landscape. What's fascinating is how these two dynamos, one buried in rock and metal, the other in searing plasma, reveal the universality of magnetic creation. Whether it's a planet or a star, the recipe is the same: rotation, convection, and conductive material. And this isn't just happening in our solar system. Exoplanets with molten cores might host similar dynamos, offering potential havens for life. Even galaxies, with their vast reservoirs of ionized gas, could generate magnetic fields through colossal versions of this process. So the next time you feel the pull of a compass needle or marvel at the sun's fiery tantrums, remember it's all thanks to the dynamo effect, nature's way of turning motion into magnetism. Up next, we'll explore how these magnetic fields shape some of the most dramatic structures in the universe: the colossal radio lobes flung across space by supermassive black holes. Now, let's zoom out to witness one of the most spectacular displays of cosmic magnetism: the colossal radio lobes unleashed by supermassive black holes. At the hearts of active galaxies, these gravitational monsters don't just devour matter, they transform it into magnetized plasma jets that stretch millions of light years across the void. Picture a cosmic fire hose blasting charged particles at nearly the speed of light, sculpting space itself into vast, glowing lobes. Take Cygnus A, a galaxy over 600 million light-years away, as a prime example. Its central black hole, weighing in at over 2 billion times the mass of our Sun, acts like a particle accelerator on a galactic scale. As material spirals toward the black hole, intense magnetic fields coil around it, channeling some of the infalling plasma into twin jets. These jets slam into the surrounding intergalactic gas, creating shock waves that light up in radio wavelengths, forming lobes so enormous they could span our entire Milky Way dozens of times over. What's truly mind-bending is how these magnetic structures persist for millions of years. The jets don't just dissipate, they're reinforced by the black hole's spin and the surrounding magnetic fields, creating self-sustaining loops of energy. The particles within these lobes spiral along magnetic field lines, emitting synchrotron radiation, a telltale glow that reveals the invisible magnetic architecture. But Cygnus A isn't unique. Across the universe, similar radio lobes trace the footprints of supermassive black holes, mapping how magnetism shapes galaxies on the grandest scales. These structures aren't just cosmic curiosities, they're key to understanding how black holes redistribute energy and matter, seeding future star formation and even influencing entire galaxy clusters. So the next time you gaze at a radio map of the cosmos, remember, those faint, sprawling lobes are more than just remnants of violence. They're magnetic masterpieces painted across the canvas of space by the most powerful engines in existence. Up next, we'll journey back to the dawn of time to unravel one of magnetism's greatest mysteries: how the first magnetic fields in the universe might have formed. Now, let's rewind the cosmic clock to a time before stars, before galaxies, even before light could travel freely. This is where we confront one of the deepest puzzles in astrophysics. How did the universe's very first magnetic fields emerge? Picture the infant universe, a seething plasma so hot and dense that particles couldn't even form atoms. In this chaos, tiny quantum fluctuations might have sparked the earliest magnetic seeds. One leading theory suggests these fields were born during cosmic phase transitions, moments when the universe cooled dramatically, like water freezing into ice. As symmetries broke in the early plasma, swirling electric currents could have generated weak but pervasive magnetic fields, stretching across the entire cosmos. Another idea ties magnetism to the universe's explosive growth spurt, inflation. In this scenario, quantum ripples during inflation stretched to cosmic scales, carrying with them imprints of primordial electromagnetic waves. These wouldn't be the strong, organized fields we see today, but more like faint whispers woven into the fabric of space-time. Over billions of years, gravity would amplify these whispers, twisting and compressing them into the magnetic structures we observe in galaxies and clusters. Yet mysteries remain. Why do even the most distant galaxies, those formed just 500 million years after the Big Bang, show evidence of magnetic fields? Did they form later, seeded by the first stars and supernova, or were they truly primordial, baked into the universe from its first moments? What's astonishing is that these ancient fields, however they arose, became the scaffolding for everything that followed. Without them, gas couldn't have collapsed efficiently into galaxies, stars might never have ignited, and cosmic rays would streak unimpeded across space. Magnetism isn't just a feature of the cosmos, it's a foundational force, as essential as gravity or light. As we piece together this cosmic origin story, remember, every magnetic field you encounter, from fridge magnets to galactic jets, is a descendant of those primordial ripples. And that's a thread connecting us directly to the universe's fiery birth. Next, we'll see how these invisible forces shape one of the sun's most breathtaking phenomena, solar prominences. Now, let's turn our attention to the sun, where magnetic fields paint some of the most dramatic displays in our solar system. Solar prominences are like the sun's own fiery artwork, massive loops of glowing plasma that arch hundreds of thousands of kilometers above its surface. These breathtaking structures don't just appear at random, they're sculpted by the sun's powerful magnetic fields, which act like invisible cages, trapping superheated gas in elegant, curving lines. Imagine the sun's surface as a bubbling cauldron of charged particles constantly in motion. When magnetic field lines rise from below, they twist and tangle, creating loops that punch through the sun's outer layers. Plasma, made of electrified hydrogen and helium, gets caught in these loops, following the magnetic paths like cars on a roller coaster. The result, towering ribbons of glowing gas that can linger for weeks, suspended in defiance of gravity. But these magnetic traps aren't always stable. When the fields become too twisted or strained, they can snap, unleashing colossal eruptions called coronal mass ejections. In just minutes, a prominence can explode outward, hurling billions of tons of plasma into space at millions of kilometers per hour. The Solar Dynamics Observatory, or SDO, has captured these events in stunning detail, revealing how magnetic chaos transforms into some of the most violent storms in our solar system. What's fascinating is how these eruptions connect back to Earth. When a prominence's debris reaches our planet, it can trigger dazzling auroras or disrupt satellites and power grids. So next time you see footage of these fiery arcs dancing above the sun, remember, it's all guided by the same invisible force that shapes galaxies, protects our planet, and even flickers in your refrigerator magnet. Up next, we'll explore how magnetic fields don't just shape stars, they also drive vast rivers of material between them, in the form of galactic winds. Now, let's zoom out from the sun and into the vast expanse of galaxies, where magnetic fields play a surprising role in shaping something far larger: galactic winds. These aren't gentle breezes but colossal rivers of gas and energy, blasted outward by the explosions of dying stars. Supernova, the violent final acts of massive stars, send shockwaves through their surroundings, heating gas and hurling it into intergalactic space. But here's the twist: magnetic fields act like invisible guides, shaping these winds into structured flows that stretch across thousands of light years. Take the Milky Way's own Fermi bubbles, for example. These towering structures, discovered by the Fermi Gamma Ray Space Telescope, rise 50,000 light-years above and below our galaxy's center. They're filled with high-energy particles and hot gas, likely driven by ancient supernova or even the supermassive black hole at our galaxy's heart. What's fascinating is how magnetic fields within these bubbles help channel and contain the energy, preventing it from dissipating chaotically. Instead, the fields sculpt the winds into coherent, bubble-like forms, like cosmic fingerprints of past eruptions. But galactic winds do more than just look impressive, they're cosmic recyclers. As these magnetized winds surge outward, they carry heavy elements forged in supernova, scattering metals like iron and oxygen across interstellar space. This enrichment is crucial for future generations of stars and planets, seeding the raw materials for rocky worlds like Earth. Without magnetic fields, these winds would lose their structure, dispersing metals unevenly and altering the chemistry of entire galaxies. So the next time you gaze at the night sky, remember, even the spaces between stars are shaped by invisible magnetic forces, weaving a story of destruction, rebirth, and the hidden architecture of the cosmos. Up next, we'll see how these fields leave their mark on something far smaller, dust grains drifting between the stars. Now, let's turn our attention to something seemingly small but incredibly revealing, the dust scattered between the stars. These tiny grains, no larger than a fraction of a human hair, hold a secret. They align with the Milky Way's magnetic fields like cosmic compass needles. As starlight passes through these aligned dust grains, something remarkable happens. The light becomes polarized, vibrating in a preferred direction. This subtle effect allows astronomers to map the invisible magnetic fields threading our galaxy, revealing their structure and strength in stunning detail. The Planck mission, a space telescope designed to study the universe's oldest light, played a pivotal role in uncovering this hidden magnetic tapestry. By measuring the polarization of light from dust across the Milky Way, Planck provided the most comprehensive map of our galaxy's magnetic fields to date. These fields don't just wander randomly, they follow the spiral arms, twist around dense clouds, and even stretch between stars, shaping the very fabric of interstellar space. What's truly fascinating is how this polarized dust acts like a cosmic breadcrumb trail. By analyzing the direction and degree of polarization, scientists can trace how magnetic fields influence star formation, guide the flow of gas, and even protect delicate molecules from being torn apart by radiation. Without these fields, the dust grains would tumble chaotically, and the Milky Way's grand spiral structure might look very different. So the next time you see a dark patch in the night sky, remember, it's not just empty space. It's a canvas of magnetically aligned dust, quietly painting the invisible forces that sculpt our galaxy. Up next, we'll dive into the extreme environment around black holes, where magnetic fields unleash some of the universe's most energetic phenomena. Shifting our gaze to the most extreme corners of the cosmos, let's explore the incredible dance between black holes and magnetism. Around these cosmic monsters, magnetic fields don't just exist, they become engines of unimaginable power. Picture a spinning black hole dragging spacetime around it like a whirlpool. Now imagine magnetic field lines trapped in that whirl, twisted and stretched to their limits. This is where the magic happens. The Penrose process, named after physicist Roger Penrose, reveals how energy can be stolen from a black hole's rotation. Here's how it works. Particles near the event horizon get caught in the black hole's spin, and some are flung outward with more energy than they came in with. It's like a cosmic slingshot, but the real powerhouse is the magnetic field. Those twisted field lines act like colossal wires, channeling this stolen energy into jets of plasma that shoot out at nearly the speed of light. These jets are among the most energetic phenomena in the universe, stretching for thousands of light years. They're so powerful they can outshine entire galaxies. And it's all thanks to the black hole's magnetosphere, a frenetic zone where gravity and magnetism collide. Without these magnetic fields, black holes would be dark, silent predators. Instead, they become brilliant beacons, shaping galaxies and seeding the cosmos with energy. What's even more mind-bending is that we've seen this in action. The supermassive black hole at the heart of Galaxy M87, famously photographed by the Event Horizon Telescope, shows these very jets in stunning detail. Its magnetic fields are so strong they can accelerate particles across cosmic distances, proving that even in the darkest places, magnetism lights the way. Up next, we'll uncover how magnetic fields leave their mark closer to home, in the delicate glow of zodiacal light. Now, let's turn our attention to something closer to home, a subtle yet mesmerizing phenomenon in our own solar system. Have you ever noticed a faint, ethereal glow stretching across the night sky just after sunset or before sunrise? That's the zodiacal light, a delicate veil of sunlight scattered by countless tiny dust particles drifting between the planets. But here's the cosmic twist. Magnetic fields play a hidden role in shaping this celestial spectacle. These interplanetary dust grains aren't just floating randomly. Many of them carry a slight electric charge, and as they do, the sun's magnetic field gently nudges them into alignment. Picture billions of microscopic compass needles, all tilting in response to an invisible force. This alignment causes the dust to scatter sunlight in a specific way, creating that soft, pyramid-shaped glow we see from Earth. What's fascinating is that this isn't just a pretty light show. The zodiacal light is a clue to the solar system's history. These dust particles are remnants of asteroids and comets ground down over billions of years. By studying how they interact with magnetic fields, scientists can trace the evolution of our cosmic neighborhood. And here's a fun fact: the zodiacal light isn't unique to Earth. Any planet with a clear view of its own interplanetary dust could see a similar glow. Imagine standing on Mars, gazing up at a faint band of light painted by the same magnetic forces that shape our own skies. Next, we'll dive into the rhythmic heartbeat of stars and how their magnetic cycles create sunspots and stellar storms. Now, let's shift our gaze from the quiet glow of interplanetary dust to the dynamic surface of stars, where magnetic fields paint a far more turbulent picture. The Sun, our closest star, has a heartbeat of its own, an 11-year cycle of rising and falling magnetic activity, marked by the appearance of dark blemishes called sunspots. These spots are like cosmic bruises, regions where twisted magnetic fields suppress the star's fiery plasma, creating cooler, darker patches. But here's the twist: the Sun isn't alone in this rhythmic dance. Other stars across the galaxy exhibit their own versions of magnetic cycles, some even more extreme. Take, for example, stars like HD 819-0, which swings through its magnetic cycle in just 2 years, or the sluggish 60-year rhythm of stars like 61 Cygni. These variations hint at the complex interplay between a star's rotation, internal dynamo, and the strength of its magnetic fields. Then there's the curious case of the Maunder minimum, a period in the late 17th century when the Sun's spots nearly vanished for decades. This wasn't just a solar quirk. Astronomers have spotted similar lulls in other stars, dubbing them Maunder minimum analogs. These stars suddenly go quiet, their spots fading as if their magnetic engines stalled. Studying these cosmic pauses helps scientists unravel how magnetic fields can flicker or even temporarily shut down, with potential clues about the Sun's future behavior. What's truly fascinating is how these starspot cycles ripple through space. A star's magnetic activity can flare into violent storms, battering nearby planets with radiation, or, in quieter phases, offer calmer conditions. For worlds orbiting these stars, the difference could mean the survival or collapse of budding atmospheres. Up next, we'll venture into the voids between galaxies, where faint magnetic threads might weave through the universe's emptiest realms. Now, let's journey into the vast, seemingly empty expanses between galaxies, where whispers of magnetism might still linger. While we often think of magnetic fields as tied to stars, planets, or galaxies, there's growing evidence that even the universe's loneliest voids aren't entirely devoid of them. These intergalactic fields are incredibly faint, billions of times weaker than Earth's magnetic field, but their very existence raises profound questions. How did they form, and what could they tell us about the cosmos's hidden history? One leading theory suggests these ghostly fields were seeded by the earliest galaxies, whose violent outflows, supernova explosions, and quasar winds could have sprayed magnetized plasma into the voids. Over billions of years, these weak signals might have stretched and diffused, leaving behind a barely detectable imprint. Alternatively, some researchers propose even more exotic origins, like phase transitions in the early universe or interactions involving dark matter, though these ideas remain speculative. The challenge lies in detecting such feeble fields. Astronomers hunt for subtle clues, like the way they might polarize light from distant quasars or bend the paths of ultra-high-energy cosmic rays. Projects like the Square Kilometre Array radio telescope aim to map these elusive fields, potentially revealing whether they're cosmic fossils from the universe's youth or something even stranger. What's at stake? If these fields exist, they could reshape our understanding of how magnetism pervades the cosmos, not just in bustling galaxies, but in the quietest corners of space. Up next, we'll see how magnetic fields stir chaos and order in the turbulent seas of space plasma. Turning our attention to the chaotic dance of charged particles in space, let's explore how magnetic fields act as invisible conductors of cosmic turbulence. Plasma, the fourth state of matter, makes up nearly all the visible universe, from the scorching gas around black holes to the tenuous winds between galaxies. But without magnetic fields, this plasma would be pure chaos. Instead, these fields weave through it like cosmic rains, sometimes calming the storm and other times whipping it into frenzy. Take the solar wind, for example. As this stream of charged particles races outward from the sun, magnetic fields embedded within it can either suppress turbulent eddies or amplify them, dramatically changing how energy gets distributed. When fields are strong and orderly, they act like shock absorbers, smoothing out plasma fluctuations. But when those field lines twist or break, a process called magnetic reconnection, they unleash violent instabilities that can hurl particles to near light speeds. These instabilities aren't just academic curiosities. They shape how heat travels through galaxy clusters, influence the birth of stars in turbulent clouds, and even determine how efficiently black holes spew jets of plasma across millions of light years. Simulations show that without magnetic fields, the universe's plasma would behave like a pot of boiling water with no lid, utterly unpredictable. Yet thanks to magnetism, energy transfers in ways that sculpt everything from auroras to the largest structures in the cosmos. Next, we'll see how these magnetic threads might even weave through the universe's emptiest voids, connecting galaxies in a hidden web of force. Now let's stretch our imagination to the grandest scales of the universe, where magnetic fields may be quietly orchestrating the spin of entire galaxies. Recent research suggests that the vast cosmic web, those enormous filaments of gas connecting galaxy clusters, might not just be passive highways of matter. Instead, their rotation could be subtly guided by the universe's large-scale magnetic fields. Like invisible hands turning a cosmic kaleidoscope, scientists have long wondered why galaxies often spin in preferred directions, as if some unseen force were aligning them. One compelling theory points to magnetism woven into the fabric of the cosmic web. As these filaments funnel gas into growing galaxies, their embedded magnetic fields could transfer angular momentum, nudging galaxies to rotate in sync with the field lines. Imagine a river gently twisting a leaf as it floats downstream, except here the river is a million light-year-long filament and the leaf is an entire galaxy. Evidence for this comes from observations of polarized light traveling through intergalactic space. When light passes through magnetized regions, its waves align in specific directions, revealing the hidden architecture of these fields. Some studies even suggest that galaxies along the same filament tend to spin in similar orientations, hinting at magnetism's subtle influence, yet mysteries remain. Are these alignments strong enough to overcome the chaotic motions of galaxy collisions and mergers? Or do magnetic fields merely whisper suggestions that some galaxies choose to follow? Simulations show that while gravity remains the dominant force in shaping the cosmic web, magnetism could be the unseen choreographer, adding a delicate spin to the universe's grand dance. Next, we'll ponder an even more elusive question. Could magnetic fields hold clues to the nature of dark matter itself? Now, let's venture into one of the most tantalizing mysteries of the cosmos. Could magnetic fields hold the key to unraveling dark matter? While dark matter remains invisible, its gravitational pull shapes galaxies and bends light. But what if it leaves behind subtle magnetic fingerprints too? Some theories suggest that certain types of dark matter particles, like actions or weakly interacting massive particles, might interact with magnetic fields in ways we could detect. Imagine dark matter as a ghostly crowd moving through a room. You can't see them, but if they occasionally brush against a magnetic curtain, they might create ripples. Scientists are exploring whether these ripples could manifest as faint, unexpected signals in sensitive detectors. For instance, if actions, hypothetical particles that could make up dark matter, pass through strong magnetic fields, they might transform into photons, leaving behind a whisper of light we see OULD Chinese letter. Experiments like the Action Dark Matter experiment are already hunting for these elusive signatures. Meanwhile, observations of distant galaxies sometimes reveal unexplained magnetic patterns that don't align with visible matter alone. Could these be traces of dark matter's hidden influence? It's a long shot, but if proven, it would revolutionize our understanding of both magnetism and the universe's missing mass. Of course, the challenge is immense. Dark matter barely interacts with ordinary matter or light, let alone magnetic fields. Yet the mere possibility keeps researchers probing deeper, turning magnets into cosmic dark matter detectives. Whether these clues lead to a breakthrough or another dead end, the pursuit itself reminds us how much we still have to learn about the invisible forces sculpting our universe. And with that, we've explored all 30 ways magnetic fields shape the cosmos, from guiding newborn stars to perhaps even revealing the secrets of dark matter. If you found this cosmic journey as mind-bending as we did, don't forget to hit like, subscribe, and ring that notification bell for more deep dives into the universe's greatest mysteries. Let us know in the comments which magnetic marvel left you the most awestruck. Until next time, keep looking up. From the birth of stars to the whispers of dark matter, we've journeyed through 30 incredible ways magnetic fields weave their invisible threads across the cosmos. Think about it, these unseen forces shape everything from the fiery eruptions on our sun to the delicate spirals of distant galaxies, even guiding the very particles that light up our polar skies. They're the universe's silent architects, turning chaos into structure and mystery into revelation. But here's the thrilling part, we've only scratched the surface. What other magnetic marvels are hiding in the depths of space? Could there be magnetic monsters lurking near black holes, or undiscovered fields threading through the voids between galaxies? The cosmos is brimming with puzzles waiting to be solved, and magnetic fields might just hold the keys. So tell us, which cosmic magnetic phenomenon blew your mind the most? Was it the star-forging power of molecular clouds, or the way Earth's magnetosphere shields us like an invisible force field? Drop your favorites in the comments. We'd love to geek out with you. And if you enjoyed this cosmic ride, don't forget to hit like, subscribe, and ring that bell so you never miss our next deep dive into the universe's wonders. Until then, keep your eyes on the skies and your curiosity charged, because the next magnetic mystery could be revealed and